Hello guys, today we're going to practice some resonance structure problems. But before we do, let me tell you about resonance itself. So with resonance, we do not move atoms around in space. We only focus, our only focus is the pi system. So the double bonds and the non-bonding pair of electrons. So what do I mean by pi system and the non-bonding pair of electrons? So here's the pi system, which makes up this double bond, and the non-bonding pair of electrons in this molecule on the left, which we call acetate ion, are this, here, and here. So what does a resonance structure look like for this molecule over here? Let me show you. So it looks like there is two resonance structures for acetate ion, and the way we show resonance is by arrows. As you can see, here's an arrow and here's an arrow. In the beginning, I also mentioned that we only focus on non-bonding pair of electrons, which are these, and the pi system, which is right here. And you can see that over here the pi system is broken, and the a pair of electrons are donated to this oxygen, and we can see that on the right here that these are the pair of electrons that were broken from this pi system. Also, the non-pair electrons on this oxygen makes up the pi system here, as we can see on this structure on the right here. The acetate ion has two resonance structure, and they both exist in nature inequivalent. So one does not win over the other, and we can test that by laboratory tests and see that, and we see that the this negative charge is shared equally between this oxygen and this oxygen. So yeah, let's move on. And it's not always true with a few other resonance structure. Just to let you know, they're not all exist equally in nature. Alright, so let's move on to this example, carbonate ion. And the way we're going to show the resonance structure, like we did before, is with arrows. So let's move these two lone pairs of electron and make a pi system here. And since I want to make a pi system here, I have to break a pi system here and give the lone pairs electrons to this oxygen to follow the octet rule for this carbon. So let's draw that. So we have a carbon, oxygen here stays the same, 1, 2, 3, 4, 5, 6 with a negative charge. The oxygen on the right has only a single bond, and now it has a pair of electrons, an extra pair of electrons with a negative charge. And the oxygen here on the top now has two bonds, a pi system, and only two pair of electrons now. So here's another resonance structure for the carbonate ion here. There is actually one more resonance structure for the carbonate ion, and is involved with this oxygen. So let me show you a different color. Let me use red this time. So this oxygen can also give its pair of electrons and make a pi system here. Since it does that, the pi system here breaks down and donates its pair of electrons to this oxygen. So let me show that with the drawing, what actually happens. So this carbon attached to this oxygen, which now is has one single bond and 3 pairs of electrons now with the negative charge. This carbon, this oxygen here on top we did not touch, so it stays the same with the negative charge. But this oxygen now has 2 double bonds with 2 pairs of electrons. So we can see that here's 1, 2nd, and 3rd resonance structure for a carbonate ion. So there are 3 resonance structure for a carbonate ion. Alright, so let's move on to a few other examples. Here, this molecule on the left, we're dealing with a radical molecule, and that just means that this molecule, usually molecules, especially a carbon molecule, comes with pairs of electrons, but in this molecule there is a non-pair of electron. So there's one electron with this carbon, which makes this whole molecule radical. And the way we draw the resonance structures for radicals is we show it with the single arrowhead. So to make a pi system, we show a half arrowhead going towards this to make a pi system, and also we would need another electron, which we're going to take from here. So in this bond and this bond right here, let's imagine that there's 2 electrons, so we would take one of the electrons and draw it with the half arrow diagram to make a pi system here between C4 and C5. And what happens to this non-bonding pair here? So, what actually happens to this one is it's given to this C4 carbon. So let's draw this structure actually. So this carbon number 1 stays the same, so hydrogens. So like I said in the beginning, molecules don't move around, so all the molecules are the same. I'm just going to draw the hydrogens first, so 2 here, and that's it for the molecules. And now between carbon C4 and C5 we now have a double bond. On the C3 carbon, we took this non-bonding pair electron and gave it to C3, so we have to show that with a dot. That's 1 electron, and C1 and C2 pi system we did not touch, so we'll keep that as it is. So here's the second resonance structure for this radical molecule, and it looks like we have one more resonance structure here, and let's draw that. So the C3 carbon is where the non-pair electron resides, so we take that with the half arrowhead and try to make a pi system between C2 and C3, and we get another electron from here and transfer it there. And so what happens to this electron? So this electron is actually given to C1 carbon with a half arrow diagram shown like that. And let me draw the final structure here at the bottom. So like I said, molecules are all the same. So we draw the molecules of hydrogen where they belong. C4 has 1 hydrogen, C5 has 2, and C4 and C5 stay the same. There is a double bond now between C2 and C3, so we draw that here. And there is a non-bonding electron on C1 now, just like that. Alright, yeah, so you can see there are 3 resonance structures for this radical molecule. Alright, let's continue with our examples. Here we have this molecule. Let's draw the resonance structure for it. So first, let me draw the